The existing switchboard's amp interrupt capacity, also known as AIC, rating is not explicitly stated. However, the main breaker is rated at 100,000 amps interrupt capacity, and the existing plans specify 100,000 amps interrupt capacity bus. Therefore, it is reasonable to assume that the existing board is rated at 100,000 amps interrupt capacity. The available fault current is expected to be around 20,000 amps. This is significantly lower than the existing board's potential 100,000 amps interrupt capacity rating. If 42,000 amps interrupt capacity rated breakers are installed, the board will not be in violation of any codes or standards in a remodel condition. According to the National Electrical Code, also known as NEC, the amp interrupt capacity rating of a circuit breaker must be equal to or greater than the available fault current at the location. In this case, the available fault current is expected to be 20,000 amps, which is less than the 42,000 amps interrupt capacity rating of the breakers planned for installation. Therefore, the installation meets the National Electrical Code requirements. Installing 42,000 amps interrupt capacity rated breakers and the existing 100,000 amps interrupt capacity rated switchboard will not violate any codes or standards in a remodel condition. The reduced available fault current makes the higher breaker rating acceptable. When evaluating the suitability of circuit breakers for an electrical system, several factors must be considered. Firstly, the available fault current at the point of installation is paramount. This value represents the maximum current that the system can deliver under fault conditions. The circuit breaker's amp interrupt capacity rating must equal or exceed this available fault current to ensure safe and effective interruption of the fault. Secondly, the voltage rating of the circuit breaker must be compatible with the system voltage. Using a breaker with an inadequate voltage rating can lead to catastrophic failure. Thirdly, the continuous current rating of the breaker must be sufficient to handle the normal operating current of the circuit without tripping. Overloading a breaker can cause it to overheat and eventually fail. Fourthly, the trip curve of the breaker should be coordinated with other protective devices in the system to ensure selective tripping. Selective tripping minimizes the extent of the outage by isolating only the faulted circuit. Fifthly, the environmental conditions in which the breaker will be installed must be taken into account. Factors such as temperature, humidity, and corrosive atmospheres can affect the breaker's performance and lifespan. Sixthly, the physical size and mounting configuration of the breaker must be compatible with the existing switchboard or panel board. Space limitations may restrict the types of breakers that can be used. Seventhly, the listing and labeling of the breaker must comply with applicable standards. Look for Underwriters Laboratories, also known as UL, or other recognized testing laboratory markings to ensure that the breaker has been tested and certified for its intended use. Eighthly, consider the life cycle cost of the breaker, including initial purchase price, installation costs, and maintenance requirements. More expensive breakers may offer better performance or longer lifespan, which can offset the higher initial cost. Ninthly, consult with a qualified electrical engineer or electrician to ensure that the selected breakers are appropriate for the application. They can perform a thorough analysis of the system and provide recommendations based on their expertise. Finally, document all decisions and calculations related to the breaker selection process. This documentation can be valuable for future reference and troubleshooting. When evaluating the available fault current, it is important to obtain accurate information from the utility company or a qualified electrical engineer. The available fault current can vary depending on factors such as the size and configuration of the utility grid, the impedance of the service transformer, and the length and size of the conductors. Using outdated or inaccurate fault current data can lead to improper breaker selection and potentially dangerous situations. If the available fault current exceeds the amp interrupt capacity rating of the existing switchboard or panel board, several mitigation strategies can be considered. Firstly, current limiting fuses or reactors can be installed upstream of the switchboard to reduce the fault current. Secondly, the service transformer can be replaced with one having a higher impedance to reduce the fault current. Thirdly, the switchboard or panel board can be upgraded to one with a higher amp interrupt capacity rating. Fourthly, a series-connected rating may be applied if the upstream overcurrent protective device is properly rated. Fifthly, a properly applied surge protective device, also known as SPD, may mitigate the effects of the fault current. The National Electrical Code provides detailed requirements for the selection and installation of circuit breakers. Article 240 covers overcurrent protection, including the amp interrupt capacity rating requirements for circuit breakers. Article 408 covers switchboards and panel boards, including the requirements for amp interrupt capacity ratings. Article 110 covers general requirements for electrical installations, including the requirements for listing and labeling. It is essential to consult the latest edition of the National Electrical Code and any applicable local codes to ensure compliance. In addition to the National Electrical Code, other standards may apply to the selection and installation of circuit breakers. Underwriters Laboratory Standard 489 covers molded case circuit breakers and circuit breaker enclosures. Institute of Electrical and Electronics Engineers, also known as IEE, Standard 141, also known as the Red Book, provides recommended practices for electric power distribution and coordination of industrial and commercial power systems. National Electrical Manufacturers Association, also known as NEMA, standards provide guidance on the design, testing, and application of electrical equipment. It is important to be familiar with these standards and any other applicable industry standards. When selecting circuit breakers for a remodel project, it is important to consider the existing electrical system and any changes that have been made over time. The original design documents for the system should be reviewed to determine the amp interrupt capacity ratings of the existing equipment and the available fault current at the time of installation. Any modifications or additions to the system should be carefully evaluated to determine their impact on the available fault current and the amp interrupt capacity requirements. If the existing documentation is incomplete or unavailable, a qualified electrical engineer can perform a short circuit study to determine the available fault current at various points in the system. This study should take into account all relevant factors such as the utility source, the service transformer, the conductors, and any other equipment that may contribute to the fault current. The results of the short circuit study can be used to select appropriate circuit breakers and other protective devices. When installing circuit breakers, it is important to follow the manufacturer's instructions and any applicable codes and standards. The breaker should be properly mounted and connected, and all terminations should be tightened to the specified torque. The breakers should be tested to ensure that they are functioning properly and that they will trip under fault conditions. The installation should be inspected by a qualified electrical inspector to ensure compliance with all applicable requirements. Regular maintenance of circuit breakers is essential to ensure their continued reliability and performance. The breakers should be inspected periodically for signs of damage or wear, and any loose connections should be tightened. The breakers should be tested periodically to ensure that they are tripping properly. Any breakers that are found to be defective should be replaced immediately. A written maintenance program should be established and followed to ensure that all circuit breakers are properly maintained. In summary, selecting and installing circuit breakers requires careful consideration of several factors, including the available fault current, the voltage rating, the continuous current rating, the trip curve, the environmental conditions, the physical size, the listing and labeling, the life cycle cost, and the applicable codes and standards. Consulting with a qualified electrical engineer or electrician can help to ensure that the selected breakers are appropriate for the application and that they are installed and maintained properly. Remember to prioritize safety when working with electrical equipment and to follow all applicable codes and standards. The available fault current, also known as AFC, is a crucial parameter in electrical system design and safety. It represents the maximum amount of current that can flow in a circuit during a short circuit condition. Understanding and accurately determining the AFC is essential for selecting appropriate overcurrent protection devices, such as circuit breakers and fuses, to ensure the safety of personnel and equipment. Several factors influence the AFC at a given point in an electrical system. Firstly, the utility source's capacity and impedance play a significant role. A larger utility source with lower impedance will generally result in a higher AFC. Secondly, the service transformer size and impedance affect the AFC. A larger transformer with lower impedance will contribute to a higher AFC. Thirdly, the length and size of conductors influence the AFC. Longer conductors and smaller conductor sizes increase impedance, which reduces the AFC. Fourthly, the presence of motors and generators can contribute to the AFC during a fault. These rotating machines can act as temporary voltage sources, feeding current into the fault. Fifthly, the system's configuration and grounding method affect the AFC. Different grounding methods, such as solidly grounded, impedance grounded, and ungrounded systems, have different AFC characteristics. Calculating the AFC requires a thorough understanding of the electrical system and its components. Short-circuit studies are typically performed to determine the AFC at various points in the system. These studies involve complex calculations that take into account the impedance of all components in the circuit. Several software programs are available to assist with short-circuit calculations. These programs use sophisticated algorithms to accurately model the electrical system and determine the AFC. The results of the short-circuit study are used to select overcurrent protection devices with adequate amp interrupt capacity ratings. The amp interrupt capacity rating of a circuit breaker or fuse must be equal to or greater than the calculated AFC at its point of installation. Failure to select devices with adequate amp interrupt capacity ratings can result in catastrophic equipment failure and potential safety hazards. In addition to selecting appropriate overcurrent protection devices, other measures can be taken to reduce the AFC in an electrical system. These measures include increasing the impedance of the service transformer, using current-limiting reactors, and implementing selective coordination of overcurrent protection devices. Increasing the impedance of the service transformer reduces the amount of current that can flow during a fault. Current-limiting reactors are devices that are inserted into the circuit to increase impedance and reduce the AFC. Selective coordination of overcurrent protection devices ensures that only the faulted portion of the system is isolated during a fault, minimizing the impact on the rest of the system. The National Electrical Code provides specific requirements for AFC calculations and overcurrent protection device selection. Article 110.24 requires that the available fault current be field marked on equipment. Article 240 covers overcurrent protection, including the requirements for amp interrupt capacity ratings. Article 408 covers switchboards and panel boards, including the requirements for amp interrupt capacity ratings. It is essential to consult the latest edition of the National Electrical Code and any applicable local codes to ensure compliance. In addition to the National Electrical Code, other standards provide guidance on AFC calculations and overcurrent protection device selection. Institute of Electrical and Electronics Engineers Standard 141, the Red Book, provides recommended practices for electric power distribution and coordination of industrial and commercial power systems. Institute of Electrical and Electronics Engineers Standard 242, the Buff Book, provides recommended practices for grounding and bonding of electrical systems. National Electrical Manufacturers Association standards provide guidance on the design, testing, and application of electrical equipment. It is important to be familiar with these standards and any other applicable industry standards. Accurate AFC calculations are essential for ensuring the safety and reliability of electrical systems. Consulting with a qualified electrical engineer can help to ensure that the AFC is properly calculated and that appropriate overcurrent protection devices are selected. Remember to prioritize safety when working with electrical equipment and to follow all applicable codes and standards.